Hello everyone. I'm Nicholas, and today, we're venturing into the heart of epidemiology by exploring the critical measures of occurrence. Understanding these measures is vital to accurately interpreting the distribution and frequency of diseases within populations. In epidemiology, we go beyond mere case counting, we're the sleuths unraveling the complex web of disease patterns. Today, we will discuss two critical epidemiological concepts when studying diseases: prevalence and incidence. These might sound complicated, but they help us understand how diseases spread among people. Prevalence provides a snapshot of a disease's current state within a population, showing how many people are sick at a specific time. Prevalence is the total number of disease cases in a population at a specific point in time, usually presented as a percentage. While sometimes referred to as a rate, prevalence technically lacks a time unit, distinguishing it from actual rates. We look at prevalence in two ways: point prevalence and period prevalence. Point prevalence is like a snapshot showing how many people are at a specific time. We find this by dividing the number of people sick now by the total population. For example, the HIV prevalence in South Africa is nearly 18%, versus less than 1% in other countries. Finally, as it calculates the number of cases at a given time, we won't see how many new cases are developing among our population. Hence, we won't see how fast the disease is spreading. It's important to note that it has no units. It is a percentage of the number of cases in the population commonly expressed in a given year. Sometimes, it is called the prevalence rate, but this name can be misleading as it is not a rate and is not expressed per unit of time. In this example, we have individuals A, B, C, D, and E, followed by 10 years. If we analyze the point prevalence in December of year 7, we can see that only B developed the disease, while A and E were healthy. This population comprised 3 persons, A, B, and E, with only one case, B. Hence, the prevalence was 1/3 or 33.3%. Note that we missed in the analysis C, who was lost in year 4, and D, who died in year 3 of follow-up. Note that the prevalence will change if we analyze other points in time. The other type of prevalence is the period prevalence. It measures the number of existing cases and the number of new cases over some time. This is especially handy for diseases with insidious starts, such as mental illnesses, as we won't be sure when the disease has started. In this case, we won't be able to differentiate between new and existing cases. Also, period prevalence won't be very useful for planning health actions, as we can't see how fast the disease develops in our population. To estimate the prevalence, we can multiply how often new cases happen by how long the disease usually lasts. Many things can change prevalence, like how good our treatments are, how many people die from the disease, and if people are living longer or shorter lives. Because of this, it's hard to compare how common a disease is in different places or times because many things can affect it. For example, fewer people will have the disease if we find a good treatment, such as TB treatment. But if more people start dying from the disease, such as Ebola virus infection, or if people don't live as long, fewer people will have the disease over time. The prevalence will tend to increase if there is a life-saving treatment such as HIV treatment. There will be people with the disease living more. Understanding why the number of sick people changes in the same place can be tricky. Incidence gives us a look at how many new cases of a disease appear. We talk about two kinds: incidence risk and incidence rate. Incidence risk, also called cumulative incidence or probability, is defined as the number of new cases over a period divided by the population initially free of condition at the beginning of the same period. It is used in static populations and for relatively uncommon conditions, which could be defined as those affecting less than 10% of the population. If these conditions are not left, people affected by the disease could be counted as initially free and counted in the denominator when they should not. In those cases, the incidence rate is better. In this example, we have individuals A, B, C, D, and E, followed by 10 years. If we analyze the incidence risk in December of year 10, we can see that D and E developed the disease, while B was diseased at the beginning of the study period. Hence, this population comprised 4 persons, A, C, D, and E, with 2 cases, D and E. Hence, the incidence risk was 2/4 or 50%. Incidence rate relates the number of new cases to the person time at risk. This measure typically uses person years as the time unit, making it particularly useful for dynamic populations, common diseases, and recurrent conditions. Incidence measures, which track the number of new cases, are crucial for designing healthcare interventions and assessing the effectiveness of prevention strategies. Moreover, the incidence rate is valuable for studying the causes of diseases and is an excellent tool for monitoring repeated disease occurrences in the same individual. This is because the group of people at risk may change throughout the study period. And how is person time calculated? First, we tally the total person time at risk. Second, we identify the number of new cases that emerge during the study period. Lastly, we divide to compute the incidence rate. Take, for example, a study involving 3 individuals focusing on the incidence rate of pneumonia. Imagine one individual is monitored for 6 years but moves away in good health and loses contact. Another individual is observed for 4 years before falling ill. The third individual is watched for 10 years and remains healthy. Here, the combined person time at risk amounts to 20 years. With one recorded case of pneumonia, the incidence rate is calculated as 1 case per 20 person years. Imagine we're dealing with 2 rates, one is 4 cases per 7 person years, and the other is 13 cases per 27 person years. Comparing these directly can be challenging due to their uneven denominators. To simplify the comparison, we standardize the denominators to a round number, preferably a multiple of 10. By adjusting the rates to have common denominators, we can easily compare them, making these different rates effectively equivalent for analysis. Hence, these 3 rates are equivalent. To simplify and better understand a rate of 4 cases per 7 person years, we can break it down into more relatable terms. Starting with 4 cases per 7 person years, we convert this to a rate per single person year by calculating 4 divided by 7, which equals approximately 0.571 cases per person year. To make this even clearer, we scale it up to a standard measure of 100 person years, resulting in 0.571 times 100, or approximately 57.1 cases per 100 person years. Hence, a rate of 4 per 7 person years is the same as 57.1 cases per 100 person years, making it easier to comprehend and compare. In this example, we have individuals A, B, C, D, and E, followed by 10 years. If we analyze the incidence rate in December of year 10, we can see that B, D, and E developed the disease. Patient A was 10 years free of disease, B and C 5 years each, D 2 years, and E 3 years. This population had 25 person years of follow-up. Hence, the incidence rate was 3/25 or 0.12 cases per person year. Key points to remember: incidence helps us look at what causes diseases and how to address them, especially for sudden illnesses. Prevalence helps us see the big picture of chronic diseases and how much care people need. Understanding these concepts, we can better tackle diseases and keep people healthy. Thank you.